This video is on solving modulus problems. I've dedicated a video to this topic like the book. I'm basically just going to go through a few past exam questions. I just want to make one pre-note. It's coming for a question to say something like the equation f of x is equal to k, where f of x is some sort of modulus, and then k is some sort of constant. It could also be something like f of x is equal to g of x, again where f of x is a modulus and g of x is something like x plus k, again where k is a constant. And it will say that this equation either has two solutions, one solution, or zero solutions. If it has two solutions, it will look like this, where there are two points of intersection. If there's one solution, it will look something like this, where there's 1 point of intersection. And if there's zero solutions, it will look something like this, where the lines don't touch each other at all. And using this information, you may have to either find the exact value of k if it's one solution, or a set of values for k if it's two or zero solutions. And the key to this is the minimum point of the modulus. If there's one solution like this, if its f of x is equal to k, the line must touch y is equal to f of x at the minimum point here. This is sometimes the case for when f of x is equal to g of x. So for something like this, x plus k, this is the case, it has to touch the minimum here. But if the gradient is really big, for example, if the line looks something like this here, it touches only 1 point and it will never meet this line again, as it keeps going further and further away from it. This is again why I talked about in the modulus function video, why a good sketch is really important. And if there's zero solutions, at the x coordinate for where the minimum point is, so this is going to be here, the line here must lie below the modulus at this point for there to be zero roots. So it lies here, the modulus minimum point, and the line is here, and the modulus minimum point lies here, and the line at this point lies here. It has to lie below the modulus at that point. We'll see all of this in the upcoming questions. So here's an example question where we're told the equation f of x is equal to k has exactly one root. So this is going to be, as this is f of x, this is going to be when 2 of 5 minus x plus 3 is equal to k, like this, and this only has exactly one root. And this is going to be, as we talked about before, this is going to be this line here where y is equal to k. This is going to be where there's 1 point of intersection, because all the other ones are going to have 2 points of intersection except for this one down here. So how do we find this line? Well, this is the minimum point of this equation, and this minimum point will exist when this modulus is the smallest it can possibly be, and the smallest this modulus can possibly be is 0, because remember that it can't be negative numbers, it can't be -1, stuff like that. So this modulus is going to equal to 0, and this is where this minimum point is going to lie, and therefore we can rearrange this in order to find k. So this modulus is equal to 0 at this minimum point, so it's going to be 2 of 0 plus 3 is equal to k, so therefore it's going to be k is equal to 3. So this line here is when y is equal to 3. And this is a solution for where there's only one root. Now, for this particular question, I haven't actually seen this much before. There is actually another set of values for where there's only one solution. And this is because of this domain here, where x is bigger than or equal to 0. See this point here? This is the last point of the modulus. This doesn't keep going on forever because of this domain here. To the point where if we do a line like this, this will only have 1 point of intersection here, as normally it would have 2 here and here, but this point isn't included here, so it's just going to be this point of intersection here. So all of these k values, y is equal to k, will also only have one solution, and to do this we need to find this y-intercept here. So this is going to be when it's 0, so it's going to be f of 0, which is equal to 2 of 5 minus 0 plus 3, which is equal to 2 of 5 plus 3, which is equal to 10 plus 3, which is equal to 13. So this y-intercept is at 13, so therefore all of these lines can exist with 1 point of intersection when k is bigger than 13. It's not when k is bigger than or equal to 13, because this is x is bigger than or equal to 0, so this point here is included, and if we draw a line here it will have 2 points of intersection, but anything higher than this will only have 1 point of intersection. So the solutions for the possible values of k is when k is equal to 3 for this line here, or when k is bigger than 13, so it can be lines like this where there's only 1 point of intersection. So for part B, we need to solve the equation f of x is equal to a half x plus 10. So as this is f of x, it's going to be when 2 of the modulus of 5 minus x plus 3 is equal to a half x plus 10. So as I talked about in the first video on solving equations like this, it's always good to draw a diagram. So if we say that 10 is about here, because this is the y-intercept, the gradient here is a half and the gradient here is 2, as this will times the x. Therefore this will have a lower gradient, so it will look something like this, where there are 2 points of intersection. Now it specifically says this diagram is not to scale, so it's not 100% there might be 2 points of intersection. So you should probably check at the end, but we'll go by assuming at the moment that there are 2 points of intersection. So we talked about again how to solve these equations. First of all, we want to make the modulus a subject. So it's going to be 2 of 5 minus x is equal to a half x plus 7, and then divide both sides by 2 to get the modulus of 5 minus x is equal to a quarter x plus 7 over 2, and then we consider when this expression inside the modulus is positive and when it's negative. So when it's positive, it's going to be 5 minus x is equal to a quarter x plus 7 over 2. Move the 5 onto the other side to get minus x is equal to a quarter x minus 3 over 2, and then move the quarter x onto the other side to get minus 5 over 4x is equal to minus 3 over 2, and therefore x is going to be equal to, if you put minus 3 over 2 divided by minus 5 over 4 in your calculator, or figure it out, it's equal to 6 over 5. So this is one of the values of x, and then the other one is when this expression in the modulus is negative. So this is going to be minus 5 minus x is equal to a quarter x plus 7 over 2. So this is going to be minus 5 plus x is equal to a quarter x plus 7 over 2. So move the minus 5 onto the other side to get x is equal to a quarter x plus 17 over 2, and move the quarter x onto the other side to get 3 over 4x is equal to 17 over 2. So therefore x, if you figure it out, is equal to 34 over 3. So we have got two suspected x values, 6 over 5 and 34 over 3, and we probably want to check it again because this diagram is not to scale, so it might not actually look like this. Well, the way we can check it again, we talked about this in the first videos, of the way that we can check this is by considering the lines individually. So when this expression is positive, it's going to be this line here, because this is the line y is equal to 5 minus x. You can see because it's got a negative gradient, and we talked about before that this minimum point exists when x is equal to 5, because this is when this modulus is equal to 0, and this modulus is equal to 0 when it's 5 minus 5, so x is equal to 5. So this is basically the domain for this line. Anything less than 5 on this side, and 6 over 5 is less than 5, so this is a solution. And then for this side here, this is when the expression is negative here. This is the line of x minus 5 or minus 5 plus x, because it's got a positive gradient, and this is when x is bigger than 5 and 34 over 3 is bigger than 5 as well. So these two solutions are valid because of this check that we've done by considering the two lines individually. So the set of possible values of k, or x, sorry, is x is equal to 6 over 5 and x is equal to 34 over 3. So for part C, it talks about this transformation here, y is equal to 4f of x minus 1. It talks about the vertex on the graph, which, if you don't know what that is, it's the corner, basically, of the graph. So it's this minimum point here. And it talks about the coordinates p and q, and this is this kind of vertex minimum point. And it wants us to find, basically, the minimum point after we've done this transformation here. So this minimum point, we've kind of alluded to this already, is 5, 3, where the x coordinate is 5 and the y coordinate is 3. And then we need to perform this transformation to see what this point becomes. Okay, so remember how to do multiple transformations is the order that we do the transformations is kind of the order in which they affect x first. So firstly, it's going to be x minus 1, and then it's going to be times by 4. So we do the x minus 1 first, so this is going to be y is equal to x f of x minus 1. This is an inside the function translation, so it's going to shift everything to the right by 1. So this is going to look something like this here. Everything is shifted to the right by 1, so this here is going to be shifted to the right by 1, so this is just going to become 6, 3, like this. And then we perform the transformation for f of x minus 1, and this is going to move everything up the y-axis by a factor of 4, so this is going to look something like this here, where everything is moved up by a factor of 4. Now this is as well moved up by a factor of 4, so this is still going to be 6 because it's still the same x coordinate, but this now is going to be times by 4. So this is going to be 6, it's moved up by a factor of 4, so now it's going to be 6, 12. And this is the final coordinate. When we do the transformation y is equal to 4f of x minus 1, this is the minimum point, 6, 12, so it's in the form PQ, so therefore P is equal to 6 and Q is equal to 12, and that's the final answer. So here's another question. This time when we have f of x is equal to g of x, where f of x has a modulus and g of x is a function of x that involves this constant k, and we're told that it has no roots and we need to find the set of possible values for k. Now, as I said in the very first video on this topic, again, it's very important or really useful to draw a diagram for these sorts of questions. So first of all, let's draw f of x is equal to the modulus of 3x minus 4 plus 3. And the first thing that we should do is draw the graph of 3x minus 4 without the modulus, and then draw the modulus from that. So this is the graph of 3x minus 4, where we have the roots at 4 over 3 and we have the y-intercept at minus 4. And now we can sketch the graph of the modulus of 3x minus 4. So remember how this works, that anything that is below the x-axis gets reflected on top of the x-axis. So this part here is fine because this is on top of the x-axis, but this part here isn't, so it gets reflected on top of the x-axis like this here, and the root is the same, and this y-intercept is minus 4 down here, it's reflected in the x-axis, so this y-intercept is now 4. So this is the graph of the modulus of 3x minus 4, so then to sketch the graph of the modulus of 3x minus 4 plus 3, we therefore just shift everything up by 3. So this is the graph of f of x, where the y-intercept was originally 4, so now it's going to be 7 as it shifted up by 3. And then the graph of g of x, this has a gradient of 1, whereas this line had a gradient of 3. So this is going to look something like this, where it has a lower gradient like this. And this is an example of g of x because it has no roots, so it has no points of intersection. So this is an example of g of x. Now, we talked about before, the only way that this is going to have no roots is the x coordinate at this minimum point. This point has to lie below this point, because if it doesn't, and it's something like this, for example, where at this x coordinate this point is above this point, this is going to have 2 points of intersection. So it has to lie below this point. So the question is now, what is the highest that this line could be where it would still have no roots? And the answer to that is this line just below this line, where this line touches the graph at this minimum point and has 1 point of intersection. Anything below this line will have no roots, so therefore it's anything just below this line here and just below this minimum point. So anything below this minimum point. So it's going to be an inequality like this, where it's below this line, not equal to, because this is where there's going to be 1 point of intersection. So probably the most useful thing to do now is to actually find this minimum point. So this again is going to be when this modulus is equal to 0, as we talked about before, because this is the lowest value that the modulus can be, as it can't be negative. So this is going to be the minimum of this function. So this is going to be when this expression is 0, so 3x minus 4 is equal to 0. So 3x is equal to 4. So x is equal to 4 over 3, and the y coordinate is just when we sub in 4 over 3 into this, which is going to be, we know that this modulus is going to be 0, so it's just going to be 0 plus 3, which is equal to 3. So this minimum point is at the x coordinate 4 over 3 and the y coordinate 3. So this is this minimum point, and this line at this x coordinate 4 over 3 has to just lie below 3. If it lies on 3, it has 1 point of intersection. Anything below it has 0 points of intersection. So 3, and then we sub in 4 over 3 into this line here. So it's got, because it's at this point, so it's going to be 4 over 3 plus k. And it has to lie below 3. Anything below 3 is fine at this x coordinate for it to have 0 points of intersection. Move the 4 on the 4 over 3 to the other side to do 5 over 3 is bigger than k, and this is the set of possible values of k when 5 over 3 is bigger than k. Anything where k is less than 5 over 3 means that this line lies below this minimum point at this x coordinate, and therefore this line has 0 roots. So this is the final answer, where k is less than 5/3. So here's one final example that we'll go through. So we have this function here, f of x is equal to 2e to the power of x minus 5, and we need to sketch y is equal to f of x. Now, this is actually a multiple transformation question because we have this graph, e to the power of x, which we already know how to sketch, and we need to apply these two transformations. So remember how multiple transformations work, is we do whatever affects the graph first. So it's first times by 2 and then minus 5. So the first transformation we're going to do is y is equal to 2e to the power of x, which is going to look something like this, where it goes up the y-axis by a factor of 2. So it's going to look something like that here, where this is y is equal to 2 e to the power of x. It says we need to show the coordinates where it crosses the coordinate axis and the equation of the asymptote. The asymptote won't change because it's still y is equal to 0, as 0 times 2 is still 0. But this is 1, but as it's gone up by a factor of 2, this y-intercept will now be 2 instead. So this is the graph of y is equal to 2e to the power of x. So the graph of 2e to the power of x minus 5 will be shifted down the y-axis by 5, so it's going to look something like this here, like that, where the asymptote has gone down by 5, so it's going to be here now, and then 0 minus 5 is just minus 5, so the new asymptote is at y is equal to minus 5. The y-intercept was at 2, but it's gone down by 5, so the y-intercept is now minus 3. And it also crosses the x coordinate axis now, which is very easy to figure out what this is, because this is going to be when y is equal to 0, so we just set this to 0. So y is equal to 0, so it's just going to be 0 is equal to 2e to the power of x minus 5, so it's going to be 2e to the power of x is equal to 5, so it's going to be e to the power of x is equal to 5 over 2, so it's going to be the natural log of 5 over 2 is equal to x. So this root here is the natural log of 5 over 2. And then this is the final answer, where this is y is equal to f of x. This is the sketch of the graph. And then for the second part, we need to sketch the graph of y is equal to the modulus of f of x. So recall back to the first video how this works. When we do the transformation, the modulus of f of x, it reflects anything that is under the x-axis in the x-axis, and it comes on the top. So this here is fine because this is on top of the x-axis, so this remains the same and is unaffected. But all of this here is reflected on top of the x-axis, so it's going to look like this here, like that, where this was minus 3, but it's reflected in the x-axis, so up here it's just going to be 3, and there's going to be a new asymptote here, and this asymptote is going to be, it was at y is equal to minus 5, so as it's reflected in the x-axis, it's now going to be y is equal to 5 instead. So this is the graph y is equal to the modulus of f of x, where the root remains the same as it still crosses at this point. So that's the final answer. So for part B, we need to deduce the set of values for which f of x is equal to the modulus of f of x. And we can just use the graph for this easily. So we need to find the set of values for which f of x here is equal to this. And this is all of this area of the graph here. When it goes under the x-axis, they split off in their own directions, but everything here is completely fine. They're the exact same graph. And this is after the natural log of 5 over 2, this root here. So this is when x is bigger than or equal to, because remember this is the root 0 and they both have the same root, the natural log of 5 over 2. Anything after this, they're the exact same graph like this, so this is the final answer. So for part C, we need to find the exact solutions of the equation f of x is equal to 2. So let's sketch a line at y is equal to 2, and this will look something like this, where this is y is equal to 2. And we can see by looking at this that there are 2 points of intersection, so there are going to be 2 solutions, which makes sense for a modulus graph. So we can probably just solve this by actually just looking at this equation. So it's the modulus of f of x, so this is going to be the modulus of 2e to the power of x minus 5 is equal to 2, and we can just consider when this expression is positive and when it is negative, because we talked about this is how we solve modulus equations. So firstly, let's consider when this is positive. So this is going to be 2e to the power of x minus 5 is equal to 2. So it's going to be 2e to the power of x is equal to 7. So it's going to be e to the power of x is equal to 7 over 2. So x is going to equal the natural log of 7 over 2. So this is one solution, and then we consider when this expression is negative. Again, go back to the first video if you don't know what I'm talking about how to solve modulus equations, but we consider when this expression is positive and negative. So this expression is going to be negative, so it's going to be minus 2e to the power of x minus 5 is equal to 2. So this is going to be minus 2e to the power of x plus 5 is equal to 2, because we expand the brackets, and this is going to be minus 2e to the power of x is equal to minus 3. This is going to be e to the power of x is 3 over 2. So therefore x is going to be equal to the natural log of 3 over 2. So x is equal to the natural log of 7 over 2, and x is equal to the natural log of 3 over 2, and those are the two solutions, and that's the final answer.